minutes. I'm just making sure if someone did not get the big idea of 10.3 that you're able to talk about it quickly in your groups, but we're about to grade our evens. So if there's any other like big concept-y someone, you're like, oh man, they're lost. Try to explain what's going on in just with 10.3, but then let's go specific to evens. So like 1 more minute as I answer Hannah's question.
I was just wondering because the homework was different. Test is it mostly?
It's because, remember, our book is introducing everything in Chapter 10. So 10.4, 10.5, what I've combined in one section is basically all the convergence and divergence tests, which you've already done. So our Chapter 10 is taking the Chapter 9 OT, Chapter 10 intro, and applying it in random bits and pieces and places. Because I'm teaching you the new stuff, and then there are things coming into homework from old. Focus more on the notes as far as new things, but realize things that showed up in homework that were review, you'll be expected to know. Does that make sense? Kind of like with harder integration, stuff comes back from, right? And so you have to know that in order to know the new stuff. Is that cool? Yeah. And that might also answer your question, Justin, if you were thinking the notes with 10.1 and there's some stuff from Chapter 9 OT, that might be why it felt weird too. But Arian was saying the same exact thing, so. All right, guys, let's go ahead and check the evens. I would love to get into questions ASAP. So number 32, you guys can see, oh my goodness, they actually derived it. That's brutal. But you can see all of your different derivatives, but here's the final polynomial here at the end, the third degree polynomial for letter A. For letter B, they were asking for, I think, the 22nd derivative, which meant you need to define the pattern and then plug and chug, not actually take 22 derivatives. Oh, please, Lord, no. And their final answer was plugging the 22nd derivative into the coefficient, which, as you guys can tell, it definitely follows the pattern from up above. And then letter C was talking about error. Now, with the error and the fourth derivative, and the maximized value of the fourth derivative. Do you see how 1 second they were like, hey, the fourth derivative is sine, and the next second the sine is just gone? What is sine maximized at? What's the one that I use sine as the example in like the majority of, ooh, this could get weird, and if it gets weird, just bound it by the closest integer you know. What's sine bounded by? 1. Sine goes between 1 and -1. The highest sine can go is 1. So instead of thinking about like the interval that they're talking about between 0 and 1/10 and, oh, sine goes up, so sine of 1/10 is the maximum value, forget it. I don't know sine of 1/10. Do you know sine of 1/10? 1. Got it. Done. Like E, make it 3.
Yeah, that was one of my questions. It's
Yeah.
like on all of these, especially there's a lot where Lagrange with the
Maximizing thing.
sine and cosine. And it was fine with cosine. Yeah, and I was plugging 1, but for this one, for this example,
Yeah.
I was confused because sine of 1 is 0. So if I plug in 1 for z, then I get 0 on top.
Oh, no. Don't plug in Z is 1. Plug in what sine is maximized by, which is 1. Like for the entire sine, not for the Z, for the sine of Z. You know how like in the AP FRQs they said that the whatever derivative is bounded by 0.2 or bound, and we just plugged that in? That is Z, we plugged it in.
Literally plug in 1.
Yeah.
Dang.
Right?
Changes everything.
Because otherwise, literally, I think is this centered at 0? It is, right, guys? Yeah, it's centered at 0. So the interval would be 0 to 1/10. Literally, the maximum value on 0 to 1/10, that would be my C to my A, would be sine of 1/10. I plug it in, it's a decimal. We're using our calculator to do the Lagrange error bound. That's not the point. The point is to have, oh, okay, then we can just go 1. Yeah, we're not using sine of 1/10 as our maximum. We're using sine and cosine, the actual function bounded by the value of 1 for the whole function. Letter D was going back to power series. Did you guys notice that? Like section 10.2, that we can integrate term by term. So you were going back to your third degree Taylor polynomial and you were integrating the terms using power rule. Is that good? Number 40 was D. Number 42 was B.
Oh, yeah.
And I did not give you many evens. Okay. Okay, I have my book open. If you guys don't mind, after grading, let's just go back to the beginning of 10.3, odds and evens, working our way through in order. Is that cool?
If we had any questions on 10.2, can we also ask? Or no?
Yeah, have we already graded 10.2? But we didn't go over the actual questions.
I just had like 2, and it didn't really help me with
The answer key that was posted, because the answer key was posted for both. Got it. Okay, sorry, I had to refresh because last week got really weird and out of order. Actually, can you guys let me know what would be better? Would it be better to go back to 10.2 questions and start there, then 10.3, building up to Lagrange? Okay, 10.2. Let's go there then. Remember, just in case for some reason you missed all the announcements last week and you didn't read Google Classroom, 10.2 and 10.3 answer keys for the evens, and then you guys had the odds in the back, were posted online, hence why we're just going to homework questions. I guess I could have done that with 10.3 also, but anyway. Section 10.2. All right, let's start at the beginning. Any questions on the first page, which would be 1 through 23? 13? Anything else besides 13, 1 through 23-ish? 11, Justin? 7. Okay, let's just start at 7.
All right, never mind.
Oh, but Justin, 7 is actually a really good question. This is a great AP question. I know that's random, but I didn't assign it. But guys, there is no special Maclaurin for tan inverse. Oh, our book does do a tan inverse. That's lame. Okay, that's true. I added it. It's up above. It's up there. But tan inverse is the integral of 1 over 1 plus x squared. So you could have built 1 over 1 plus x squared and then integrated term by term. Or you can memorize tan inverse. You could have used tan inverse's derivative, or you could have used 1 over 1 plus x and plugged in x squared, which probably would have been easier, I guess. If they want 1 over 1 plus x squared, you'd have to derive the tangent inverse one, because the derivative of tangent inverse is. Does that make sense? Yeah. Sorry, but then number 11 and 13 are the 2 that I saw. Okay. Number 11, how'd you guys build it? Oh. For G. Yeah, 1 over 1 minus x.
For 11?
Because what you could do, 1 over 1 minus x, like ignore that, right? We'll bring that in a second. 1 over 1 minus x would go to 1 over 1 minus x cubed, so plug in f of x cubed. And then multiply everybody by x. So Hannah, this goes back kind of to those weird ones. Oh, this is 10.2. Luciano. Justin, go ahead, though, while I'm showing this.
I just was asking because I need help finding the general term.
Got it. And then Hannah, you were curious about how it got built. I would go there to there and then to there by 1 over 1 minus x. That's the geo series, right, guys? With r equal to x. So it's 1 plus x squared plus x cubed, which, Justin, that would be x to the n as my nth term. Oh, that doesn't help you. Sorry.
How do you go from the first step to the second step? That's my issue. Like, I feel like you would multiply by x for the third part, but like, how do you get that?
F of.
Oh, so then you multiply the.
Not multiply, plug in. Does that make sense? Because it'd be x cubed and then x cubed squared. Power to a power you multiply. So then it'd be x cubed to the n, or I would say x to the 3n. So I'm kind of building the general term too. Does that make sense? And then times x. That's what you were saying, Riley. So then times, and Hannah, does it make sense? I'm just multiplying the whole thing by x, which means I can distribute. So x plus x to the 4th plus x to the 7th. Now this gets a little bit nastier, but Justin, think about it. What did we just do? We multiplied the old general term by x. So then we could make it, I don't know, x to the 3n plus 1 is probably what I would have done.
Can you do that for 8, the general version?
Yeah. So 8, 7x is being distributed, sorry, to e to the x. E to the x is the funny dude that's, every derivative is the same, right? So that'd be x squared over 2 factorial. Is that e to the x, guys?
Yeah,
Sorry, I have not rememorized these.
that looks right.
So it'd be x to the n over n factorial, right, is the e to the? X to the n over n factorial. Yeah, so it'd be 7x plus 7x squared. I'm just going to do dot, dot, dot. Well, hold on, I want a factorial. Sorry. 7x cubed over 2 factorial. So then that'd be 7x times x to the n over n factorial. See? And now I can just do it as 7x to the n plus 1 over. Got him.
Did you have to do that?
Was there a general term? I think they were asking for the general term.
Yeah, but like if I just did 7x times x to the n, like the one right above it,
Yeah, but
do we have to say?
for an FRQ, this would have been sufficient, but a multiple choice, they're going to make it nice.
Gotcha.
Yeah, they're going to make it nice. Does that help with, no, number 13 was a new section, wasn't it? Find the Taylor series generated by the function given by.
I feel like now that I practice more, I think I know how to do it, so I was just confused if x equals 2, so that's the center then? Or no?
At the given point, generated by the function at the given point. Yeah, that's your center.
Okay, thank you.
That's the question.
Although with that being your center,
I just subtracted by 2. It's like the same. Can't you just?
you can plug in x minus 2 for your x term.
That's all.
But with your derivatives would need to be at 2 instead of at 0. I don't think you can use the Maclaurens for centering at a different point, can you?
Or can't you use? Oh,
Do
I
it
just.
like the old-fashioned way with
You have to do it the old-fashioned way with taking, hold on, here, check it. Here's an example, oh, no, example 4. Our special ones, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, is when it's centered at x equals 0.
Right.
But as soon as we have it centered somewhere else, all of our derivatives are not at 0 anymore. Now, this one, the derivative was easy because all of it was e to the, but see, it totally changes our series. Because it's not just going to be e to the 0, which is 1 in front of everybody, 1 over 2 factorial, 1 over, now it's e squared over. So, Maggie, in the sense of adding in your center here, you're good, but your coefficients are going to change because your derivatives are going to
Oh, yeah,
change.
yeah, I did the derivative. I did it.
Oh, good, you built it. You built it, okay. Sorry, so we got through the questions so far on 1 through 23. We're up to 13. Is there anything past that?
Yeah. Can you do 27C?
Okay. Anything before 27?
24. Sorry.
24.
24A.
Okay. And then 26. Oh, 16?
B, just B.
At x equals 1.
So that would be the same thing build it by hand, right?
Oh, yeah. I got it.
Yeah.
Okay, cool.
Yeah. So plug in f of and then f prime of, that's double prime of. Good. And then Naomi, yours is 24?
24A.
24a. Ooh, they give you the series. I love these ones. These ones are fun. Sorry, you probably don't think any of these are fun. This one, they gave you the series. Kiddos, does this series look familiar at all? It looks almost like e to the x, except aren't the powers off? Shouldn't that have been an x, and shouldn't that have been x squared over? Huh. Now, technically, we don't even need to... Oh, familiar function. That's mean. Anyway, A, sorry. When you're looking at this series, remember, I can take that huge polynomial and think f of 0 plus f prime of 0 all over, no, f prime of 0 doesn't have anything special, huh? F prime of 0 times x plus f double prime of 0 all over 2 factorial x squared plus f triple prime all over 3 factorial x cubed. That's where this polynomial somehow came from. Now hold on. They want f prime of 0. F prime of 0 goes with the x term, right? So what do I have? I have f prime of 0 times x somehow turned into 1 over 2 factorial times x. So can't I say that f prime of 0 must have been 1 over 2 factorial? Because in my progression, the x term, which is over 2 factorial, has the derivative times x. So if I just discount the x's, if I just simplify, then I say, okay, well, f prime is whatever's left. All right, cool. But what does that mean about the 10th derivative? Whoa, I have to keep on going? No, just find the pattern. Guys, what would the 10th derivative's term be? It would be f 10th of 0 times x to the 10th. Okay, hold on. X to the 10th, wouldn't it be over, according to the pattern, 11 factorial? So x to the 10th would be over 11 factorial, so therefore I can take away the x to the 10th. Doesn't the 10th derivative of 0, lo siento. According to my pattern, the 10th derivative, x to the 10th, is going to come from x to the 10th over 11 factorial, so therefore this guy must have been 1 over 11 factorial. Does that make sense, Naomi? And that makes sense. Pause. I just convinced you all the wrong answer. Why? Were there any factorials I had to worry about here? So hold on. Isn't this the 10th derivative of 0? What would this in the Taylor? Check it. This one was just f prime equals the coefficient, but everybody else has a little factorial in the formula. So shouldn't this have had a 10 factorial? Oh. So this would be the 10th derivative of 0 over 10 factorial is 1 over 11 factorial. So then the 10th derivative of 0 is equal to, multiply. Oh my goodness, isn't that just 1/11?
Wait, so why is it not 11 factorial, not 11 factorial?
The term from my series is this one, but the formula would have said find it this way. So the formula somehow simplified down to this, and the only way this formula could simplify to this is if I had 1 over 11 as my 10th. Because then it'd be 11 times 10 factorial, which is 11 factorial. Sorry, Naomi. Does that make more sense? Yeah. Okay. We have to make it match the formula. And then, Aryan, you said 27.
I did 27C.
Oh, sorry. Oh, yeah, Aryan, yours was the other one.
I don't, because it's h prime of x equals the function.
Oh, yeah. Now, first of all, the function we can build just by, Riley, this is your question, by plugging in. Because we can plug that x squared into this dude's special series. Do we have a special series for square root?
Well, yeah, you have square root 1 plus x. Well, no, you don't. No, you don't. I take that. But in the first problem, number 1.
You build up, right? Oh, yeah, you build up. Okay.
I got A and B, right? I did not use C.
So then let me know what you ended with B, because we need to use B for C.
For B, I got 1 plus x squared over 2 minus x to the 4th over 8 plus x to the 6th over 16.
Okay, and it was the 4th degree? First 4 non-zero terms. Oh, got it. And then find the first. So this was for G, right? Which is square root of 1 plus x squared. Okay. And we're trying to find h
But they give us h.
such that h prime.
Yeah, and then I tried taking the integral. Oh, I should just take the integral of
This
this.
is h prime. To get to h, we want to integrate. Yeah. So we can integrate term by term.
Yeah.
So the x plus
Dang, I should be fine.
x cubed over 6 minus x to the 5th over 40 plus x to the 7th all over 102? No, 112. Well, that's why power series are helpful, is because once you get a polynomial, I can derive term by term, I can integrate term by term, I can jump from a power series to that function's derivatives power series or that function's integral power series just by playing with the polynomials. Yeah.
Okay, can I ask one more question?
Yeah.
I've done a new question.
Oh, yeah.
Number 41, I'm like, you don't even understand. Because that's not, because the sign, like the special requirement. I mean, Taylor, sorry. It's supposed to be odd.
Are you thinking Maclaurin or are you thinking Taylor?
You have to build it by hand.
Yeah. Because it's centered at a different point.
Okay, that's what okay, because I was like, it's not math.
Yeah. So you were trying to do an at 0 over at pi over 2, which would be an approximate. They're like, no, move the whole thing over to pi over 2. So your x minus pi over 2 was good, but your f primes were off.
Okay.
Justin.
So going back to C,
Yeah.
basically we can just use like the Taylor polynomial that we got from that same function
Perfect.
and just integrate that.
Term by term. Yeah. Does that make sense? Good. 10.2. Anything else?
Well, I guess, never mind.
You were thinking the 40s, right?
It was
40.
42 again. But it's different. But I guess I just have to like,
If you have the one from 41, you can do the series notation.
and they played me hard.
Yeah. Because then it messed you up on 2 questions right in a row. That was really mean, actually. I apologize. 10 point. Oh, no, go ahead.
Oh, can you go back to 24C?
Yeah. Oh, see, I was wanting to go over that one, but then didn't ask. Okay.
She was just saying that you have to like build it by hand, but you can't because it's that
Oh, I gave the answer without realizing it. Justin, if it's just x times f of x, and Hannah, this is kind of like your question. If it's x times f of x, we can just multiply term by f of x's polynomial. Well, because the nice thing is if I substitute for f of x his Maclaurin, it's just a polynomial. I can just distribute. You see it? So then, I'm just going to do dot, dot, dot. If we are multiplying by x, it's just a simple distribution. So then we end up with x plus x squared over 2 factorial plus x cubed. Oh my goodness, it's e, but wait, what's missing? Isn't e to the x 1 plus x squared over 2 factorial plus x cubed over 3 factorial? Can't I just do, oh, this is e to the x minus 1. Right? Like, literally, it's knowing your special Maclaurins for the Maclaurins, not for the at in the center. Sorry, lo siento. But it's knowing the special Maclaurins and playing with them. But you can't play with them if you don't know them, which is why I had to challenge you all this weekend. Out of love and grace. Okay, so, section 10.3.
Do you want us to take, like, have people volunteer? Because I feel like there's so much time.
As far as questions. Do you think we can cover some of them? I think we can, maybe. Let's figure out, let me go to our notes. Let's write down the homework problems and see what we have. So what questions do we have on 10.3 with Lagrange? Justin? 19B? Hannah? Like directions and stuff like that? Let me get to the book and then we can powwow as people are working. Naomi?
33.
Okay. 35?
Wait, I don't need C. I take it back. I'm so sorry. I need D on that.
This one?
Yeah.
35, 21, Aryan, just 21?
Oh, actually, no, never mind.
Oh, you're good? Okay.
No B.
Just A and D. Oh, I heard you. Sorry.
Also, I'm sorry. Can you do 41?
Yeah.
Oh, wait, can you actually just do all 33? No.
Okay, well, I mean, I can say
Let's just see what we got. Can anybody do 19B?
I can do it.
Okay. Maggie, grab a spot, pull out the board. Let's try not to pull out the board. You can erase that one and use that. Just because that way I can talk with Hannah about questions. 33? 35?
don't think I can like solve it completely, but I
can do everything.
Except D. Kathy and Ari and powwow 33, because then put your two brains together. Maybe we can get all the way through D. All of you guys just erase the whole Pascal's triangle binomial theorem and just take over the board. Anyone else? 35, 41, 42. Oh, those are your questions? Did you get to start any of them?
yeah, sure.
I didn't know I did 35, 42. I got the right answer, but I don't know how.
I don't know how.
You want the scale? Sure. 43, are we supposed to do a quadratic approximation?
Let's see. Here. Because these were your questions and you have like questions on general. Let's powwow on the board. Is that cool?
Because I wasn't sure if we learned that or not.
Well, it depends on how they're asking it. Because we could do a quadratic portion of a Taylor or a Maclaurin and plug in. But I don't know if that's what they're asking. Okay. Anna, do you have anything before 35 that you want to powwow about?
I just have, so
Yeah.
formula, we did one in class where, you know how it has the x minus c to the n plus 1 part of the Lagrange error bound?
It's the yellow box, right?
Yeah.
Yeah.
So we're doing one and the x just became 1 and didn't have any.
Because we were approximating at, or using it to approximate at a value, so I plugged in x's, like we did for tangent lines or Euler's different. Well, they could ask us, like let's say it's centered at 3, they could ask us for 3.1. Or they could, like at the sign one in one of the homeworks, the 0 and the 1/10, we would have had to plug in the 1/10 if we're, like it's centered at 0, but we're approximating it at 1/10.
So the x is basically
No. The x is using the Taylor polynomial, using it to approximate at a particular x value.
is it like if they say approximate sine 0.5, would it do 0.5?
Well, where are you centered at though? What are they asking you? Perfect. So it'd be 0.5. Yeah. But if it was approximate sine of 1.5 centered at 1, you would have 1.5 minus 1. Does that make sense? Got it. So let's go look at 35. Let's see what's going on. Yeah.
See, how do I write this in approximation? It's saying like the degree, like so it's like the third degree
Yeah.
and then the fifth degree. So that's,
Yeah.
I can write it like that.
Yeah.
Even though it sounds like this, it doesn't go to 5 terms.
No, that's okay.
Okay.
Because the n doesn't stand for terms, it stands for degree.
Okay. I was like,
Oh, okay. So what I did was like this was added, right? So I just plugged in x squared like it was here.
Consider the initial value problem.
Instead of that x, I plugged in x squared. So like this 10x becomes an x squared. Correct?
I'm buying this.
I'm sorry, Ken. When'd you get sick?
Right after
Ugh. Blisters and sick. That sucks.
So for each one that was given x, since we're replacing this x with x squared, and each of these x's an x squared.
Are we calling Diba? Okay. The one that you were asking about, Riley, that was the 40s, right? With the quadratic. It was which one?
Put your face up, put your camera up. Here, let's go.
Hi, Diba.
Oh yeah, yeah.
Do you want to see my D?
U, so since like U is only x, because x squared is
Okay, it's her face on the camera, so beware.
Hi, you.
She had a face.
Hi. You hanging in there?
Yeah, she can talk. She's been able to talk.
Yeah. You feel that all, huh? You little punk. Here. Bye, Diva. Love you, miss you. There you go.
Oh my gosh.
Okay, that was so low. Your body.
What are you doing? chapter 10.
Yeah. Review. GSD, but your cheeks got massive today. When she said her sweet, I was like,
I read to
can you even
11:15.
see his T-bone?
I thought we had until 11:15. I guess we only had until 11. Is that my bad?
It's an hour behind. So it's
Oh, so confused. I'm like 11:15, not 11.
morning.
Anyway.
Oh my gosh! Wow.
All right, kiddos. Yeah, the clock's wrong. I didn't realize it until right now. That's weird. All right, guys. We're going to play tomorrow with 10-4, 10-5. Come ready, but review all of your convergence and divergence tests. Ah, you're welcome. I have 35. Oh, you're doing 33. You didn't get very far?
We just did A. We had to get.
Well, I'll go ahead and copy 33 and have it ready in the notes for tomorrow. Oh my God, Issa. Guys, 19B is over here on the sideboard. My bad. Sorry, I thought we still had another 15 minutes.